Hello, welcome on behalf of TAS International. My name is Peter Rickmeyer and I would like to discuss in this presentation about restraint models. Well, let me first give a very simple example of what a restraint is. Suppose you are opening the door. Well, you have the hinges for that. Those hinges, let's assume they have no friction and no torque friction. Those are the typical joints. But if you're going to apply a rotational spring on it, then we talk about restraints. It might have friction. That's also modeled within a restraint model. Those are the hinges, the joints. But you can imagine that those doors also have a spring between the door and the wall. That's another type of restraint. That's a restraint between two bodies. In the next slide, you'll see an overview of the restraint models which we currently have available within MADYMO. Joint restraint, it just looks like one, but actually there are a lot of them. We're not going to discuss them in detail, don't worry. Then you see 5 restraint models, which are connection between rigid body, or between a body and the reference space. That's also possible. And then there are a few special restraint models, like a belt or an airbag model. Those will be captured in a separate presentation. Muscles are another example of restraints, but those will not be addressed in the introduction training. Well, let me first explain a difference between a constraint and a restraint within MADYMO. A constraint, you can imagine that as, if you look to the left bottom picture, that's a reference joint. Each joint has 6 degrees of freedom. 3 translational, 3 rotational. Well, the constraints are the degrees of freedom which are suppressed, so not able to move. In this case of a reference joint, it's only just 1 which is able to move freely, so that means 5 are constrained. The right picture is an example of a restraint. Again, it's a reference joint. It has 1 degree of freedom which is able to rotate. That's the rotational direction. And on top of that, you can put a restraint model. In the next slide, you see an overview of restraints which you can apply on a joint. You can apply a restraint on a translational joint, a revolute joint, universal, cylindrical, planar, and the more exotic ones like a translational revolute or a translational universal. On top of that, there are a few very special restraints. Those have to be applied to spherical and free joints. And those are called cardinal restraints and flexion torsions. Cardinal restraints we're going to focus a little bit more into detail because I consider this as important. Well, how does such a restraint model look for a joint? You have to define a characteristic .load for that. Next slide you will see an example. A characteristic constraint or a characteristic .load is built up from several components. You have your loading function. That can be either linear, either non-linear. It's important to know, especially if you have a non-linear loading function, which direction is positive. Well, that's the parent joint. Besides the loading, you can also apply hysteresis, such that you can go to the unloading path as well. You can put damping on it, friction, and even rate dependency by a dynamic application factor. In this slide you see an example of a translational joint. It's an example of a steering column of a car. It's just one translational joint, which is called the steering axle joint. It's referring to a characteristic load with a loading function, and there is also hysteresis. There's no unloading function defined in this case, but that means that the unloading load is 0. Besides the elastic part, you can define damping, viscous damping. That can be split up into 2 parts. One is independent of the velocity, so that's just the damping coefficient. But if you like, you can define also a damping force which is dependent in time, so with respect to the velocity. Coulomb friction, there are several models of that. In this case we're going to discuss the standard one. The standard one is independent of the normal force. For some of the joints that will be addressed later on, you can even model more advanced stick-slip models. As you can see in the picture here, you see a ramp 1 and a ramp 2 value. Underneath, the default values are addressed, 0 and 0.5. I think this requires a little bit more explanation. The Coulomb friction is the standard one, so no slip possible, is just a force. So it is as it is. The ramp function, Fs, is explained in this picture. The Cf is the value you define as a user, and that's a constant drive friction force value. Well, typically MADYMO is used for dynamical load cases, but if you're interested in to focus on more quasi-static load case analysis, this might become relevant, because what is happening? Before the ramp 1 value, or in this case it is 0, there will be no friction force applied, even if you have defined it as a user. Then in a linear way, it is increasing up to the ramp 2 value, and after ramp 2 value, it gets the full frictional force as defined by the user. Reason for that is that if you won't apply this, you might end up in very noisy signals. And the more advanced friction models do facilitate stick-slip, but for that I do refer to the reference manual itself. One other point with respect to the ramp values is the last item on this sheet. It's about priority. You can define the ramp on a global or a local level. If you define it on the global level, so under control analysis time, it will be applied to all restraint models which don't have their own ramp values. So in case you have defined your own ramp values under the restraint joint, those will be overruled. Well, basically this has already been addressed in the previous slide. The standard Coulomb model has no stick-slip possible, and the friction force does not depend on the normal force. However, there are more advanced friction models available for the translational, revolute and spherical joint. In general, I would recommend, if you make your own models, to first set up a simple model and specify output such that you do understand how the model is working before you incorporate it into your full model. Well, the previous part basically was about joint restraints. Now we're going to focus on restraints between bodies, or a body and a reference space. Here you see an example of a 1D Kelvin element. It's a parallel spring and damper connected between two bodies. Instead of parallel, you can also define a Maxwell. It's also a 1D element, but it's also connected between two bodies, or a body and a reference space, but no, they are serial. Restraint point requires a little bit more attention. It's also a connection between rigid bodies, or one reference space, but you have to define a coordinate restraint system on the parent body. That's the way you orient it. And then on the second body, if it's a body, you have to define a point. And then orthogonal to the coordinate restraint system of the parent, you get 3 Kelvin elements. Well, the last slide, or the last point of the sheet, is about coincident point, 1 with 2. That is, looks like a simple one, but it can have a tremendous effect on your results. Basically, it means if you specify one with 2, that the coordinate system of the parent is put on top of the point P. That means that initially there will be no forces applied due to damping or springs. On the other hand, if it's off and they are not on top of each other, you will get forces. Of course, this will affect your results. The next 2 slides are the last 2 slides of this presentation, but please pay attention because it's considered as a very complicated topic. It's called the carbon restraint. Let me first explain how it works. You got 3 axes where it can rotate around. You can apply elastic torques, damping torques and friction on those torques. In the picture you see the way it's working. You've got 2 coordinate systems of the restraint, one of the parent and one of the child. Initially, let's assume they are on top of each other. Then first it's rotated around the x-axis. And then you get the situation which you see in the right top of this picture. Then we're going to rotate around the new y-axis, which is seen in the bottom left picture. At the end, you're going to rotate around the z-axis. Well, the issue is once you rotate around the second axis 19 degrees, because then something is happening that will probably result in an abort of your simulation. It's not a MADYMO specific one, because if you're going to search on the internet, you're going to find a lot of things on gimbal lock, because that's how this phenomena is called. And even the Apollo 11 moon mission has suffered of gimbal lock. Well, let's go to the next slide. Here you see a picture. Take some time to digest because it contains a lot of information. But what it basically is that the first and the third axis are in line. Because the second axis has been rotated 19 degrees. Due to this 19 degree rotation of the second axis, the first and the third rotational action can't be discriminated. And for that reason, MADYMO can't resolve the equation and will abort due to gimbal lock. Well, if you're going to apply a restraint, you're flexible in the way you orientate those axes. I highly recommend you that you take the second axis as the most stiffest one. Ideally not even crossing the 90 degrees rotation, or that might not be possible, but by defining the stiffest characteristic on the second axis, you prevent that the second axis is going to rotate 19 degrees, and due to that you're going to prevent a gimbal lock effect. Thank you for your attention. I hope it was all clear. Goodbye.